Hello physics students, welcome to the Batcave. This week we're going to look at Newton's universal law of gravitation. He's supposed to have got this idea when he was sitting under a tree at Cambridge University and an apple fell on his head, and he was supposed to think about what force causes things to fall and what's the force that causes the planets to go around the sun and the earth to go around the moon, and he believed it to be the same. It was a gravitational force. So those of you who try really hard this can actually sort of give the best efforts. The one with the best effort can win a car, not this one, and Robin, you can come with me to the classroom as well. Let's go. Okay, welcome to the Bat Physics classroom. So we're going to look at gravity, as I said here. Let's get some tools here. So it's going to be Newton's universal law of gravitation. Tom, please put that phone away. No, Robin, you can't hit him with a batarang. Yes, I know he's annoying, but still, no. Now, universal means it works everywhere. Okay, so that's the idea, that it will work outside the Earth, inside the Earth, and way away from the Earth. So a couple of things that Newton said is, if you look at something like the apple falling on the Earth, he thought that it would be dependent on the mass. The actual size of this force here depends on the mass of the object. So apples would have a different force which they knew compared to objects with more mass, like a person. So his first assumption was the force was proportional to the mass of the thing that was actually being pulled down on Earth. Now logically then, if that was the case, and we call it M1, it would also apply to the Earth, because objects that were bigger in terms of a planet would also cause more gravitational force. So if you were to take yourself up here and go to Jupiter where there's more mass, you should get more force that way. So it's proportional to both of those two. So if you put those together, it's actually proportional to the product of those, in fact. Multiply those together. So if you were to double one and say triple the other, altogether you would get 6 times the overall force. So it's a proportionality thing. Okay? So if you just sort of think about that first. Now, if you start to consider distance between the objects, he considered the distance between their centres and showed mathematically he thought it should be an inverse square law. In other words, as you went further away, the force would become weaker. Now, it wasn't an inverse law where if you went twice as far away, it became a half, which would be one way of thinking, or 3 times further away, it would become a third. It didn't do it that way around. So what you've got to think about here is he actually believed it was to be an inverse square law. In other words, it would go like this. He believed it to be an inverse square law, in other words, this sort of relationship. So he actually imagined having a piece of toast he was trying to butter with a butter gun. So you put a piece of toast like that that's a certain width across and a certain height. And we put it a certain distance away from a point source, which would be a butter gun, which would spray butter out on the piece of toast to actually go through and butter the toast. And what he said was that this is the distance between the butter gun here, the nozzle here, and the actual toast, and that was a distance d. You're covering an area of r squared there. It's basically r times by r. And what he said was, what would happen if you went twice as far away with those sort of forces, if we were talking about a point source? So if you go to twice the distance, what would happen there? And he argued that the piece of toast would actually be twice as wide there and also be twice as high, like that. And I haven't drawn that very well to scale. But the idea would be he's now covering 4 times the area, which means that the butter would only be 1/4 as thick in terms of size, the thickness would be. Now if you think of this in terms of gravitational force, his thought was that if you go twice as far away then, you should only see 1/4 because it's an inverse square law. It's going to get weaker by the same proportion, being like a point source. And that sort of follows. So if it was 3 times further away, you should be down to 1/9 of the force. Okay? If it was 4 times further away, it should be down to 1/16, and so on. So you just need to bear that in mind, that it was an inverse square law. The other way you can look at this is to think of like light doing the same thing as a point source. Now the bat signal is not exactly a good point source, but if we go back and try this out here. So if we look at something like the bat signal here, so we consider the bat signal there, if that was a point source there, if you were to sort of have the bat signal here, what sort of force would you get, given that that was the distance there? Well, it had spread over a certain area. Now this is not a square one this time, but what is the area of a circle? Let's use the maths teachers here. Because maths is just a tool, remember? 4 pi r squared. So maths is a tool for physics. Sorry about that, Mr. Turnbull. So areas of 4 pi r squared. If you go to twice as far away, you're going to get areas 4 pi r squared as well. But how much has the r changed here? Well, if you actually double this distance here, you can show that the radius of this circle here will actually have doubled as well, using similar triangles, all right, which we won't go into at the moment. So it actually works that way as well. That if you go twice as far away, you'll get 1/4 of the force because the area has spread over to 4 times the size. You've got 4 times the area of a circle, and therefore you've got 1/4 of the force. Well, in this case, 1/4 of the light. So the light intensity here, which we'll think about as being a force, would actually be still proportional to 1 over the distance squared, where you start from that point source there. So Newton basically said those things together. Now if you put those together as an idea then, it's proportional to both of the masses as a product, the inverse square law. You can come up with a formula, which they did by basically plotting graphs using some different masses that they measured the forces on a torsional spring balance. And they came up with a constant that actually came up with the formula here. It was based on the two masses, the inverse square law. They often use an R there, by the way, now. And this constant got it into newtons. So that's what we're going to talk about. So that's his overall force. It's the force between any two masses, or any two bodies. All right? So we go back here. So if you look at his universal attraction in words, you're actually looking at the fact that it's a mutual force of attraction between any two masses, so they act on each other equally. The force is proportional to the product of the masses, which means they multiply together if you do them both. And inversely proportional to the square of the distance between their centres. So that's it in words, but obviously it's a lot easier to write it as a formula. The gravitational constant is always given to you. It's universal, it works everywhere, including on Earth, and it's 6.67 by 10 to the minus 11. So if you wanted to work out the gravitational force of attraction between Batman and the Earth, you would need to know, well, let's go from my mass being 100 kilos, it's a bit over, but that'll do. The radius of the Earth is 6.4 by 10 to the 6 metres. And the mass of the Earth is 6 by 10 to the 24 kilograms, close enough. Okay? If you wanted to work out the gravitational force of attraction, the old way would have just go F equals ma. And we go, it's 100 kilos, 9.8 is the acceleration, you get 980 newtons. Alright? But using the new way here, we're going to use that force of attraction like that, G m1 m2 over r squared, or d squared if you want to do that. You get 6.67 by 10 to the minus 11. We've got a mass here for the Earth of say 6 by 10 to 24, and it doesn't really matter which way around you have the masses. And you've got a mass of the person as 100 over 6.4 by 10 to the 6. Now don't forget this needs to be in metres, and it should be squared. So you're going to get the same answer. Now why would you bother to do this technique here? Because obviously it's quicker to just do that. Well, the advantage here is, out in space, if we were to put Batman out in space further away from the Earth's surface, say 1,000 kilometres up, you could not use this formula here, because you do not know the acceleration due to gravity all that far up there. But you do know the increase in distance we're talking about and what would happen if you went that far away. And that's the sort of thing you need to know for the space program. Based on the moon's mass, how much gravity would it have there on the surface and in between the Earth and the moon? What sort of gravity are we talking about? What sort of forces are we dealing with to know how much rocket fuel they would need? You could also work out the force of attraction with Robin and Batman, but we ain't going to do that today. Now you could look at the force of attraction with the Earth and the moon then and get the same sort of thing, because this works for planets as well, don't forget. It's a universal law. So we can look at G, mass of the moon and mass of the Earth if you like. Actually I'll call that mass of the Earth. Mass of the moon over their distance between them, but you can use that as d squared or r squared. So again we've got 6.67 by 10 to the minus 11. Mass of the Earth, 6 by 10 to the 24. And mass of the moon is 7.35 by 10 to the 22 kilograms. And they're separated by a distance of 3.85 by 10 to the 8 squared. So we're going to square that distance that's in metres, and we'll end up with overall force in newtons. Alright, I'll see you in the back cave. Thanks for coming. Well, thanks for coming. I hope you enjoyed the time in the classroom. Remember to keep studying physics and look forward to other videos that are coming. Thank you very much.